Hello everyone, my name is Juan Gómez-Luna and today I'm going to present our work evaluating machine learning workloads on memory-centric computing systems. Let's start with an executive summary. Machine learning training is a computationally expensive process due to frequent accesses to memory in order to access large training datasets. This entails a data movement bottleneck that can be alleviated with memory-centric computing systems or systems with processing in memory capabilities, which have been recently manufactured and commercialized. The first one is the AVMEM-PIM architecture, and our goal in this work is to understand the potential of modern general-purpose PIM architecture to accelerate machine learning training. Our main contributions are the PIM implementation of several classic machine learning algorithms, the workload characterization in terms of quality, performance, and scaling, comparison to the counterpart implementations on CPU and GPU. We have released our source code, and we perform an experimental evaluation on a real-world PIM system with more than 2,500 PIM cores. Outcomes of our work are key observations, takeaways, and recommendations for ML workloads on PIM systems. This is the outline of our work, where we will start with some introduction to the machine learning workloads that we have evaluated, some background on processing in memory architectures, the PIM implementation of the ML workloads, and the evaluation in terms of quality metrics, analysis of PIM kernels, performance scaling, and comparison to CPU and GPU. So let's start from the beginning. Training machine learning workloads is computationally expensive because this requires accessing large amounts of training data and many iterations. And this entails frequent data movement between memory and the processing elements. And when there is not enough computation to amortize the cost of training data, we really have trouble. And this might happen due to low arithmetic intensity, low temporal locality, or irregular memory accesses. So our goal in this work is to understand the potential for general purpose PIM systems to accelerate machine learning training. We implement 4 representative machine learning algorithms that are linear regression, logistic regression, decision tree, and k-means. And all of them, as we evaluated, fall in the memory bound area of the roofline. Now let's talk a little bit about processing in memory. Processing in memory is a computing paradigm that advocates for memory-centric computing systems where processing elements are placed near or inside the memory arrays. Real-world PIM architectures are becoming a reality with AVMEM-PIM, Samsung HBM-PIM, AXTIM, SK Hynix AIM, or Alibaba HBPNM. These PIM systems have some common characteristics. First of all, there is a host processor, a CPU or a GPU, that has access to a standard main memory and PIM-enabled memory. PIM-enabled memory contains multiple PIM processing elements, and these processing elements run at a few hundred megahertz, and they have a small number of registers and a small or no cache or scratch pad. They typically need to communicate via the host processor, and this is how one of these systems looks like, where we can identify the standard main memory, the host processor, and the PIM-enabled memory with memory arrays and processing and nearby processing elements. In our work, we have used the AVMEM-PIM architecture that has general-purpose PIM cores called DRAM processing units or DPUs that can run up to 24 PIM threads called tasklets, and they support natively 32-bit integer arithmetic, but multiplication and division, as well as floating point operations are emulated. Each DPU has access to its own DRAM bank that is called NRAM and its own scratchpad memory that is called WRAM. This is how this PIM system looks, where you can see the dual socket CPU, some DIMMs of conventional DRAM, and some PIM-enabled memory. Okay, now let's talk about the PIM implementation of the ML workloads. We evaluated linear regression, logistic regression, decision tree, and k-means clustering, and these workloads show some diversity in terms of memory access patterns, operations and data types, and communication and synchronization. For linear regression, which is a supervised learning algorithm where the predicted output variable has a linear relation with the input, we have divided the training data set equally among PIM cores, and inside each of the PIM core, each PIM thread has computed dot products of row vectors and weights. In the end, the partial gradient values are reduced and sent to the host. We implemented 4 implementations of linear regression. The first one uses floating point operands. The second one uses fixed point representation, integer operands. The third one uses hybrid precision, and the last one uses a custom multiplication based on the 8-bit built-in multiplication that the AVMEM-PIM architecture supports. For linear regression, a supervised learning algorithm for classification, we have used a similar parallelization approach. In this case, we implemented 6 versions. First one with floating point, second one with 32-bit integers, third one replaces the use of Taylor series for sigmoid with lookup table, which might be in MRAM or in WRAM. Then we also have a hybrid version and a version that uses OR custom multiplication. For decision tree, we also partition the training data set equally among pin cores. For decision tree, it's especially important data layout in order to guarantee streaming memory accesses that maximize the memory bandwidth of the pin cores. And for k-means, again, we partition the data set equally over the pin cores. In this case, the pin threads need to see what's the closest centroid to each of the points in the training data sets, and finally the host will recalculate the centroids. Now let's take a look at the evaluation. In our evaluation methodology, we have used synthetic and real data sets that you can see on the screen, and we have evaluated our work on a real pin system with more than 2,500 pin cores, on an Intel Xeon CPU, on an NVIDIA A100 GPU, and we evaluate quality metrics, performance of pin kernels, performance scaling, comparison to CPU and GPU, and performance and CPU and GPU. And this is the pin system that we use in our evaluation, as I showed you earlier. So let's go with the quality metrics. So first of all, for linear regression, we observed that the training error rate of the 32-bit floating point version is the same as the CPU version. For integer version, the accuracy remains, or training error rate remains pretty close to the FP32 version. For logistic regression, we observed that the lookup table-based versions obtain even lower training accuracy than the one that uses approximation with Taylor series. And for decision tree, the training accuracy is very similar to that of the CPU version. And for k-mean clustering, we can say more or less the same. So in general, we can observe that we maintain the accuracy of all these workloads or keep it close to the CPU baseline. Now let's take a look at the performance of the pin kernels. So for linear regression, one thing that we can observe is that all versions saturate at 11 or more pin threads. We will talk again about this soon. A fixed point representation accelerates the kernel by an order of magnitude over the 32-bit floating point version. So one key takeaway is that arithmetic workloads with arithmetic operations or data types that are not natively supported by the pin cores will run at low performance due to instructional emulation. So one recommendation is to use fixed point representation without much accuracy loss if the pin cores do not support floating point. For linear regression as well, we observe that the hybrid version, the version that uses hybrid data types, is 41% faster than the 32-bit integer version. So one recommendation is to use quantization and hybrid precision. They have performed pretty well in the UpNP architecture. And we can obtain an additional 25% speed up when we use our custom multiplication. So recommendation here is that programmers or better compilers optimize code by leveraging the native instructions. For logistic regression, we observe that there is very high kernel time on the 32-bit floating point and integer versions due to sigmoid approximation, but when we use lookup tables, the performance improves by 53 times. So one recommendation is to use lookup tables memorization, that is, using pre-calculated operation results in memory whenever possible in PIM architectures. For the hybrid version, we observe 28% faster performance and additional 43% speed up for the version that uses built-in multiplications. One general observation over all these kernels is that the performance saturates at 11 tasklets. And this is in the UpNP architecture, this means that the pipeline latency hides the memory latency. So as a result, we can say that these kernels are compute bound on the UpNP architecture. And the key takeaway is that ML workloads that are memory bound due to low arithmetic intensity in CPU and GPU become compute bound when running on PIN. So one recommendation is to maximize the utilization of the PIN cores by keeping their pipeline fully busy. Now let's talk about the performance scaling. We perform strong and weak scaling experiments. Here I show you some results for the strong scaling experiments. General observation is that the PIN kernel scales linearly with the number of PIN cores, and there is a little overhead from inter-PIN core communication and communication between the host and PIN cores, which makes this platform pretty promising for these kind of workloads. So one key takeaway is that machine learning workloads with need large training data sets can benefit from the large PIM-enabled memory with many PIN cores, and even if the PIN cores need to communicate via the host processor, the amount of data movement needed for intermediate results is quite tolerable. And finally, comparison to CPU and GPU. First of all, comparison for linear and logistic regression. We observe that the PIM versions that use operations that are not natively supported by the hardware really are heavily burdened in their performance. However, the optimizations that we applied really were able to close the gap with respect to the GPU. For decision tree and k-means, we observe pretty good speedups for both decision tree and k-means, and these speedups are even better when we use an even larger data set like the Criteo 1 terabyte data set. So key takeaway number 4 is the machine learning workloads that require mainly operations that are natively supported by the PIM hardware, such as decision tree and k-means clustering, outperform their CPU and GPU counterparts. You can find many more details and results in the long archive version of our paper, and our code is publicly available in our repository. In order to conclude, let me go again over the executive summary. Machine learning training is computationally expensive due to memory-bound operation accessing large training data sets. And PIM, memory-centric computing systems, can alleviate these data movement bottlenecks. So our goal is to understand the potential of PIM for machine learning training. And as you have seen, we are contributing PIM implementation of several classic machine learning algorithms, their workload characterization in comparison to CPU and GPU. The source code is publicly available. We perform an evaluation on a real PIM system, and outcomes of our work are some key observations, takeaways, and recommendations. You can learn more about this work and other of our works on processing in memory and as well as real-world PIM architectures in our processing in memory course. You can find the links in these slides or in the tutorials that we have organized. This one corresponds to ISCA 2023, and we will organize a fully virtual PIM tutorial for Micro 2023. We also deliver many more courses on GPUs, SSDs, memory systems, bioinformatics, etc. You can access them through this link. Thank you very much for your attention. I hope you found this talk interesting.